Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni. We are going to start with chapter 4. Now, we studied in chapter 3 that the equilibrium of a single rigid body of a system connected members are treated as a single rigid body. Now, first we drew a free body diagram of the body showing all the forces externally to the isolated body. And then we applied the force and moment equation of the equilibrium. Now in this chapter, we will focus on determining the forces internal to a structure, that is the force of action and reaction between connected members. Now, in order to define this, we must understand what is an engineering structure. An engineering structure is any connected system of members built to support or transfer forces and to safely withstand the load applied to it. To determine the forces internal to an engineering structure, we must dismember the structure first, and then we are going to analyze separately using free body diagrams of an individual member. And after the calculations, we are going to combine all these members. Now, this analysis requires careful application of Newton's third law, which states, you can say, as you all know, equal and opposite reaction. Also, we are to analyze the internal forces acting in several types of structures, namely trusses, frames, and machines. In this chapter, we are going to treat or consider any statically determinate structure. This means there are structure which do not have more supporting constraints than necessary to maintain equilibrium configuration. This is the most simplified form of statically determinate structure. We have already seen in past chapters the equation of equilibrium, which were enough to solve certain problems. But in this chapter, we will face certain situations when we will have statically indeterminate structures. The analysis of the trusses, frames, and machines and beams under you can say concentrated loads constitute a straightforward application that we have developed, the methods and process we have developed in last 3 chapters. As you all remember, first by isolating the body, by constructing correct free body diagram, and to developing correct equations of statically determined structures. One of the basic structures, first thing is we're going to come up, is the plane trusses. A framework of a plane truss, you can say, is composed of members of joint at their ends to form a rigid structure. So the definition of a truss is a framework composed of members joined at their ends to form a rigid structure. You have seen these structures such as bridges, rooftops, derricks, and other straight structures, which are the common examples which we see in our day-to-day lives. The most common structure used in our you can say civil society use are I-beams, channels such as C channels, circular channels, rectangular channels, angles, bars, and certain special shapes which are used to stabilize overhead structures. Now these structures are fastened together at their ends by welding or by riveting or using large bolts, or you are sometimes using simple pins. Now we have to understand, when the members of a truss lie essentially in a single plane, we call that truss as a plane truss. For example, a bridge. Now the bridge structure is a plane truss and on either sides. So you have 2 plane trusses connected internally by beams, and over those beams we have stringers that spread across the 2 plane trusses. A special type of bridge structure which is shown here, right here, thing right here in this figure. Uh, the combined weight of the roadway and the vehicle is transferred to a longitudinal stringer. As you can see, these brown planks, their load is transferred to these joints, and this is the complete beam which is transferring the load to these joints, the two plain trusses on either side. Now the combined weight of the roadway and the vehicle is transferred to the longitudinal stringers, then to across the beam, and finally the weight of the stringers and cross beams accounted for to the upper joint of the two plain trusses, which form the vertical side of the structure. Now, a simplified model of the truss structure is indicated at the left side of the illustration, as you can see right here. So, what is a simple truss? So first thing is, what is a truss? The basic element of a plain truss is a triangle. Three bars joined by pins to the ends, as shown in the figure right here, figure A. Now these bars or these bars constitute, or this structure constitutes a rigid frame. The term rigid is used to mean, you can say that the frame is rigid in figure A. The rigid means that it is a non-collapsible, or also means that any kind of deformation in any member induced internally is negligible. On the other hand, four or more bars pin jointed to form a polygon with many sides constitutes of a non-rigid frame. Now we can make the non-rigid frame into a rigid frame, or stabilize this structure, non-rigid polygon, into a rigid structure, as you can see right here in figure B, by adding a diagonal bar in between A or D, or B or C. We can add a bar right here, or add a bar right here, forming two triangles. This will increase the stability and will make the structure rigid. We can extend the structure by adding two more, or you can say by addition of two and connected bars, such as DE and CE, AF and FD, which are pinned together to fixed joints. In this way, the entire structure can remain rigid. Now, the structure built from basic triangle in the manner described are known as simple trusses. More members are present than are needed to prevent a collapse of the bridge, or you can say, if more members, let's say when more members are present than needed to prevent the collapse, the truss is statically indeterminate. A statically indeterminate truss cannot be analyzed by equations of equilibrium alone. Additional members or support, you can say additional member or supports, are not necessary for maintaining the equilibrium configuration. In other words, you can say the additional members which are not a vital part of equilibrium, they are called redundant elements. Now, if you are to design a truss, we must first determine the force in the vertical members, in various members. Then we are going to select the appropriate size structural shapes to withstand the force. There are several assumptions involved. First one, we are going to assume that every member is a two-force member. What is a two-force member? Two-force member is always in equilibrium under an action of two forces, that is generally defined. You can say two forces on either side. You take a single element and pull on either sides. Each force is being balanced by action or reaction force. The two different the two forces applied at the end of the force have to be equal, opposite, and collinear to be in equilibrium. Now, the members may be in tension. Now, this is how the force's direction are going to change. This means the two force member can either be in tension or in compression. as you can see in the figure right here. Now, if you cut the section, you can see, assume, if we can cut the section, the same force is transferred inside the member. Now, we assume here that the weight of the member is small compared to the applied force. If it is not so, we can replace the weight of the member by two forces, and we can say on each side we have half of that weight member acting within the reaction, or the compression or tension forces, and for it can be introduced on either side of the two force member. Now, these forces in effect are treated as loads externally applied to the pin joint connections. Accounting for the weight of a member in this way gives the correct result of an average tension or compression along the member, but this will not account for the effect of bending or of the member. Now, how these trusses are connected? The trusses, as you know, can be welded or riveted. So welded or riveted connections are used mostly to join the structural member. We may usually assume that the connection is a pin joint if the center line of the members are concurrent at joints. As shown right in this figure, they are passing right in center. Sorry, my bad. Where is it? Concurrent means passing right in the center, and joints are welded joints could be taking place on the other side. We can also assume that the analysis of a simple truss that all external forces are applied to the pin connections. This condition is satisfied in most of the trusses, such as we have seen in bridge trusses, as shown in the very beginning of this presentation. Now, for large trusses, we introduced rollers, rockers, or some kind of slip joint. Some kind of slip joints, which is there to support for different thermal expansions, variable loads, or can account for change in or irregular deformation in a very big structure. But even for that, the structure, the truss, is considered to be statically indeterminate. The two methods by which two methods you can say by which we can solve these trusses are explained later on. But you have to understand, the external reactions are determined first for any structure, and by applying equilibrium equation as a whole. The force analysis of the remainder of the trusses is performed afterwards. The first thing you have to understand, we have to develop a very good free body diagram for external loads, and then we are going to carry on to the internal loads. The first method